So for this hour, I'll discuss a modern extension of the localization method. But before starting that, there is this view that might be useful. The way we set this up, and it's traditionally used, is proof by contradiction. If something you want to prove, you first assume it's false, and then you prove that in fact its implication in one dimension is actually true. So therefore, is actually the negation is true, and therefore. But there is actually a way to view this, what we did, as induction instead of contradiction, which is that you're trying to prove something about, let's say, a convex body, some measure in this way. You're bisecting it, right? So, for example, isoperimetry. There was some subset for which you wanted to prove the boundary is large. Now, suppose I bisect it so that I maintain, so this is S, right? And this is K. And originally, volume of S divided by volume of K is something, and let's say it's less than half. Okay? And therefore, I want to prove the boundary is at least volume of S times something. Now, let me bisect it such that, let me use a hyperplane cut such that this ratio is preserved. That's one inequality, one equality, which I can preserve, right? I just bisect the difference between volume of S minus constant times volume of K, and so that both sides still have the same fraction. Great. Now it's enough to prove it on both of them, because together, by induction, by sum. Now you keep doing this, right? We keep finding these bisecting things. Each piece that you get at the end in this tree that you're building has the same fraction of S. So if you could prove the target inequality on each of them, you can add it up and you're done. So that's why I'm calling it a proof by induction, because you're going to keep dividing it up. What happens at the bottom of our induction, of our division? It's a needle. That's what we proved. So if whatever you proved for needles, the aggregate is what you want to do. So it's a proof by induction. And what we're proving is proving for every needle, right? Every needle, something is true. But if you think about it, if you want to prove isoperimetry, you don't need to prove it for every needle. Let's say I prove it for half the needles by volume. Done. Other half, I don't care. I proved it for half the needles, I'm done. In fact, why half the needles? Let me prove it for a random needle, and you're done. Which plane? Well, I mean, this, as long as I'm maintaining this fraction, we're okay, right? But the needles that appear are the important. The needles that appear in this particular division. Yeah, but right. So if you could prove what you wanted for, not, I don't mean random for some oblivious measure on needles, but for the measure that shows up here, right. And so this motivates the thing. And I remember struggling with this because, there are so many bisecting planes, even for one inequality. There are so many there. So you could pick a random one, for example, even within that, and still maintain this. And so does that give you something? And it never, seemed to go anywhere till this idea that Ronan Eldon had, and that was the following. Instead of doing this very discrete thing of partitioning into two, which is one way to decompose a measure, let us actually write it as a convex combination of measures. And then you get much more flexibility. And in fact, how do you generate this convex combination? Because we want to make sure that the average of whatever measures you're coming is the original one, is the following idea. And this is stochastic localization. Now, this, we won't be able to state a lemma quite like this, okay? But there are several properties that we can abstract away, and those properties can be applied in each different context. And actually, in some sense, it gives more flexibility. Okay, so even though it's, the statement is a little less generality. So, Okay, so let me describe what, so rather than doing this partition into two, what you do is you have some density, let's say P of x, right? What I want to do to this density is I want to change it a little bit, not such so drastically, half gone, half gone. I'll change it a tiny bit. How do I change it? We'll pick a random direction, and in that random direction, we'll apply a linear reweighting. Okay, so as a result, this density will change over time, and we'll call it PTX. At any point in time, t is now time, starts at 0. So P of x is P0 of x, density, some density. And now we're going to describe the process that evolves this density. Okay. At any given point, the expectation of PTX, expectation over this process that I haven't yet defined, will still be P0 of x. So it's a martingale. The change will be 0 in expectation. And in fact, let me just state what the simplest version of this is this. So at time t, the change will make. Now this is going to be a stochastic change, right? It's not a deterministic equation. It's going to be a stochastic change, even though the measure is deterministic that we start with. It's just a function. I'm going to change it in a random way. Okay, and this will be. You look at the current mean. This is the difference, the current mean, inner product with, I'll define everything in a second. Okay. So the current density, you're multiplying by this inner product. And this is a familiar term, it's just a deviation from the mean. But I'm taking the projection along a random infinitesimal Gaussian. Okay, so this is the Wiener Gaussian process. Okay. Mu t, yeah, mu t is just the mean of Pt of x. Integral x Pt of x. So, of course, one could do courses on this, on stochastic calculus, and of course, I should probably take some of them. But here's the point is that this is a highly non-trivial object whose existence was unclear for many for a long time. But here is the point is that this Wt, right? This is a first of all, it's an infinitesimal process, right? So it's changing continuously. But at any time t, this Wt is actually just the Gaussian with variance t. Okay? And that's the funny thing, the fact that you can take a Gaussian and decompose it into a sequence of these infinitesimal increments. That was unclear. So it's useful to think of dWt as W dt, if you like. It's like a Gaussian with time only dt. These are heuristics. This is a fact. But okay. And then if you think about what is the expectation of dWt squared, that's the expectation of W dt squared. W dt is this Gaussian, so this is dt. So you see, this is a useful thing to keep track of. The square of this Brownian increment, this random increment, is proportional to the time. Right? It's the variance. Okay. Now, so that's defined. Now this is a martingale because the expectation of this is 0 because this has expectation 0. Yeah, so I already wrote that. Good. And yeah, so just it's clear just to emphasize this, the expectation of dPtx over the randomness we're introducing is 0. And so we get this sequence of distributions. Maybe useful to think of it briefly in discrete time. If I were to use not infinitesimal time increments but discrete, then I would write it as Pt plus 1 equals Pt, right? And then times what? right? That's the question. PT plus what? Times what? Yes. So x minus, so let's say the increment time corresponds. So I have to choose some finite, the one step corresponds to some finite variance Gaussian. Let's say it's h. Okay, I'm putting that out here, mu t, and then an actual Gaussian. Right? That would be the, now you see, of course, it's not exactly the same. I mean, this, for each h, it's a different thing, but this is like, e to the, 1 plus x is like e to the x minus x squared over 2, small x. So e to the, root h times this minus half h times this. Square, right? So the point is that here you're getting an x square and it's proportional to h. Okay. It's suggesting that, and the original is getting multiplied by some, okay, exponential, but the point is it's also by this Gaussian-like factor. Now this is just intuition. We shouldn't trust any of this. Let's see what actually happens. H is like in place of dt. I'm using h, but it's supposed to be, yeah, time increment, exactly. Yeah. Okay, so let's actually do this. And we want to understand what does PT look like, right? So how can we do that? So for this, we have this stochastic differential equation. And more generally, if I have a stochastic differential equation that looks like this, x is a random variable, it's changing over time, and it has some mean, some what's called drift, such as a deterministic change with time, and some random change here. This is a basic stochastic differential equation. The change in x is infinitesimally linear in some vector, and then some matrix times the Gaussian, infinitesimal Gaussian. And okay, good. So, but you see, we want to do more than this, right? We want to know what does PT actually look like, right? And so for that, there are some nice general tools. So if you given this equation like this, and this is a special case where we don't even have this mu at all, this is 0. We only have a dWt term with this x minus mu t, right? So the general formulation is this what's called this Ito lemma, which is if I have some function of xt and I want to know how does this change, then this is so you look at the gradient of f at xt times dxt. Now you would stop here with normal calculus, right? If everything was deterministic, this is it, right? This is the chain rule, right? In each coordinate, you're taking the derivative and then derivative of that variable. But as we observed here, these are different scales. The dWt is a different scale from dt. We have to look at the second term, and that one is half second term of the Taylor expansion, this increment, the Hessian of f times sigma t transpose. I really should write capital sigmas because this is a matrix, but anyway, I guess I'll just keep it like that. dt. So this is the additional thing we get because of the stochastic nature of this increment, Ito term. Right? So let's apply this right away. I mean, say more about these things, but maybe, yeah, maybe this is a fine enough description to meaningfully proceed. So let's look at specifically at using this, and then I'll switch to the other side of the board. let's look at, given this is our basic equation, let's look at what happens to log of PTX. Of course, you can ask, why am I looking at log? I mean, this is with hindsight, but playing around and you see what's the right guess. I mean, in the discrete thing, we notice that there is an exponential-like term appearing, so maybe log is a reasonable thing to consider to see the change. But anyway, let's look at this. So what is this? Now PTX is the variable, right? And we know what its equation is. So the derivative of log PTX, 1 over times dPTX, right? Just one variable, so simple so far. And then plus half, now second derivative, which gives me a minus 1 over PTX squared. Good. What about the numerator? This sigma t is x minus mu t times x minus mu t, transpose times x minus mu t now. And so it just becomes x minus mu t squared dt. Times, we still have the outside PTX squared. So let me put back everything. So this derivative of log is substituting for dpt. We are left with x minus mu t dwt. The PTX cancels, minus half x minus mu t squared dt. So you see what's happening to the log? It's changing by this random part, and then it's also changing by this deterministic quadratic part. Okay, so now, yeah. Hessian, this is just the matrix of second derivatives. And this is an inner product, so this is a matrix, but pairwise, entry-wise, you multiply and add up. I mean, if you want as a matrix, I would write it as sigma t, yeah. Yeah, it's a matrix and a matrix. So here, what I want to now do is separate the x terms, because everything else doesn't depend on x. So let's see here. From here, I'm going to get half x squared dt, okay? In some sense, this is the most important property we'll prove here. After that, other parts are technically difficult, but this is the reason why everything seems to work. So dt. And now I'm keeping the x. I'm looking at all the x terms. So what do we have for the x terms? From here we get a plus mu t dt, right? Because we get 2 times half there, and the minuses cancel. And then we have this dwt here. Okay. And then, now this covers all the x terms. I got the quadratic term here, the linear term, and the linear term here. And then I'm left with some other terms that don't depend on x, like this mu transpose dwt, and this mu t squared dt, half. Okay. Good. This is just rewriting to separate x from the rest. Now let's integrate this, right? Meaning, if I go up to some time t, what is this going to be? And so that will be log of ptx divided by p0x, log ptx minus log p0x, the change, total change, started at some p0 and went up to some pt. This is equal to, this gives you minus t over 2 x squared. This is some linear function. I'll call it ct transpose x. The integral of this will give me some vector ct, right? Transpose x. And then this part is something that does not depend on x at all. So I'll just call it g of t. But what does this mean? If I now exponentiate and take p0 to the other side, it's telling me that pt of x is equal to e to the minus t over 2x squared plus some ct transpose x, ct depend on t, and then minus gt, but let's say it's proportional to, and I get rid of the gt part, because gt doesn't depend on x, times p0. So it's the original density times a Gaussian. Now you have to rescale to make it a, that's why it's proportional, that's what the gt does. But that's it. You really see a Gaussian that's just growing larger or smaller with the variance is 1 over t, right? So as t increases, 1 over t decreases. But this factor is, so it's becoming more and more strongly log concave. That's the first observation. It's becoming more and more strongly log concave. Why is that good? Well, we saw one reason, right? Which is that we know a lot of things about strongly log concave. They're very nicely behaved for many reasons. In particular, we know the careless conjecture for them. Already true, right? So this raises a program, which is what? You want to prove something about your original measure, which is an arbitrary measure. You apply stochastic localization. You reach a nice measure for which you can prove what you want. But now you have to make sure that you can conclude something about the original measure. This imposes some constraints. How long can you go? Maybe you have to do the localization a little bit more generally. This is in some sense, this is the slight simplification that we did with INT-ATLI. But in fact, you can do this process more generally. You can put here in front of this matrix, just like here, you can put a general matrix here, which depends on the current distribution. That gives you some more flexibility and so on. So that's the process. And I'm planning to lead you through the proof of how this gets applied to prove stronger inequalities. But if you have any questions, find time to. Since we saw the difference in what's happening. Oh, I guess I'll make one more remark about the comparison and then remove that, which is, so previously we were partitioning, right? What are we doing now? We're getting a random measure, which means what? The original measure is being written as a convex combination of measures. Again, convex combination. Each stochastic step is a convex combination of measures. So you are writing the original distribution as just a convex combination of measures. And so if you could prove something with some probability over this final measure, saying something about the original measure, in principle. Okay. I guess we'll keep this part. Okay. Now, is this useful is the first question. And from this form, we can already get a nice implication. So lemma, that the covariance of PT, this covariance matrix of PT, because of the strong log concavity, it's going to be bounded by 1 over T times the identity. I mean, this gives you concentration right away. And so you can prove that the largest eigenvalues are small. That's one. It's just T, this is just a property of T strong log concavity. It's nothing to do with localization. Okay. Now the main thing is, how can we take a property that's true for PT and show it's true for P0, which is an arbitrary log concave measure? So let's try to do isoperimetry. right? So we start with an isotropic arbitrary p of x, right, which is p0 of x, and let's say it's log concave. And fix a set, I forget, I called it S or E or something. Yeah, fix some set, I'll say S, and we are interested in the boundary measure of this divided by the measure of this. Let's assume P of S is less than half. This is what we're interested in. Then we now we apply localization. So P becomes PT. Okay. Now when P becomes PT, we can consider PT of the same set. We could consider this. Now this we know is large. Okay, up to constant. This we know is large. What can we say about this? Now, in fact, we can assume for the purpose of isoperimetry, a nice theorem by Emmanuel Millman that says that it's sufficient to consider subsets of measure exactly half. Half ones will be the ones that give you the worst. It's intuitive, right? But that's actually the case. So, okay. So PS is half. Boundary of S is what you want to bound. You moved, you got these, and this is large. What can we say about this? Now, the trouble is that, yeah, what do we, the expectation of each of these is correct because they're martingales. Expectation of anything is okay, right? Any linear. Expectation of PTS, right, is just P0 of S. So in expectation, it's correct. We would be done, but it's an expectation of a ratio, right? So it's not the ratio of the expectations, right? And that's where the game is, okay? Right. So, yeah. So after you, yeah. So what's happening with this? With the absolutely, yeah. So you should eventually you have to. There has to be something else. CT is a completely stochastic random variable. That's why I call it CT. Yeah, but that doesn't affect the fact that it's strong enough. Yeah. That doesn't play a role in which. No, not really. Yeah. There are other factors we have to control, which yeah, exactly. So we couldn't go forever. In fact, what happens? Let's think for a second. What happens if you go forever? If you go forever, when t goes to infinity, that means the variance of this Gaussian is going to 0. So you're going to a point mass. So you're just decomposing the original distribution into point masses with the correct probability, okay, which is correct as well. And of course, that will tell you nothing about the original. Okay. So the game is here's how we'll play the game. The numerator will say in expectation matches, and the denominator, let's just make sure that PTS is let's say between 1/4 and 3/4. Let's go up to the time t so that PTS stays between 1/4 and 3/4. This was half, right? It only changes by, say, half, 50%. And this in expectation is a separate thing. And then we're good, right? Okay. How do we do this? So I'll just formalize this. So we're saying P0 of this boundary of S is the expectation of PT of the boundary of S. Nothing so far, but we know that this is root T times expectation of PT of S. Okay, I haven't done anything yet, but then this probability that PTS lies between, say, 1/4 and 3/4. So if we can prove this to be a constant, we're in good shape. So we want with constant probability, so we don't need to prove with high probability. Just need to show that with constant probability, you go up to a time t, ideally constant time, so that PTS stays. Yeah. Otherwise, you get point masses, right? Previously, we got in the classical lemma, we got segments because we had a constraint, right? So, yes, exactly. Yes, right. And this one, you don't want to make it, damage it. Stay close to what you started with. Right. Yeah, right. Okay. So how do we do this? So we have to understand how PT is changing now. It's not enough to look at expectation. We have to look at basically variance, right? But it's a variance of a random process, so we have to do a little bit of work, but we have the tool for it. So we'll just apply the tool. Okay. So we already know what dpt looks like. So what I really want to write down here is, what is the change in the measure of the set? Okay, I'm just writing this formally. We know the measure of a point, so this is just the integral of the change over the points in the set. So over S, x minus mu t, dwt, pt of x, dx. Right, this is PTS itself is just integral over S of p of x. dpt is the derivative of this. That derivative I just wrote down. Okay. Oh, so this is itself a stochastic differential equation, right? This is some function of the pt, dpt, right? So, right, it's a stochastic random variable. So let's write down how much it changes. In fact, it's just. I mean, I get to define any function I want when I mean, this is this is over time, right? So the change, the d is referring to time.
That's fine, but what I'm saying is that so here there was pt of x, and on the right you have pt of x.
Yeah, we use that.
So you could think of pt of x as the variable, like as x.
Right. Yeah, I mean, let's just think of this as the random variable. Right. Yeah. So this is, what is this? This is integral over S of dwt doesn't depend on S, right? It's really x minus mu t, pt of x, dx, inner product with dwt. It's just a differential equation. If you like, I can write this transpose dwt. What I mean is, this is the coefficient by which you are changing I've got myself a differential equation. In fact, it's just a martingale. I mean, it's a
variable is changing. So if I write it down, right?
This is the only variable for us now.
Yeah, pt of x.
Yeah.
But it doesn't, the things that appear on the right hand side are some other variable. Like,
I mean, this is just some
other fact.
This is just a constant that depends on t. It's just a fixed vector. Yeah, but that's a. This is a vector, yeah, it's a fixed vector. I mean, this is, let me call this some alpha t. That's it. It's just alpha t dwt. Depends on some. It depends on many things. Yeah. That's it. Yeah, it's a stochastic differential equation for pt of s. What do you mean?
Because on the right hand side you have other variables.
I mean, here is a stochastic differential equation. dxt equals 2 times dwt.
That's fine.
That's
yeah, the constant. That is not a constant. That depends upon.
Oh, it can depend on some function of.
That's fine. That's not a
time.
function of xt.
No. It can depend. No. It can be. Actually, no. It only depends on time. Function of t. Here, this is the stochastic differential equation. This is a function of stochastic differential equation.
Yeah, this I agree.
And that's what this is.
No, but that's not what it is, because there's a dependence upon pt of.
It's already integrated.
It's integrated, but I don't. These variables are there, right? I mean,
No,
they're also time varying variables. So I had a system of differential equations, one for each x.
Yeah.
Right? So that's what we had. We didn't have one single stochastic equation. We had a sequence of SD, one for each.
It so happens the PTs are changing over time. Yes.
Yes, but they are changing in a. I mean,
in some coordinated way.
in a coordinated way.
Doesn't matter. So I'm not restricting how this FT appears, right? This FT is some function of time alone. Does not depend on X. You know, it's some function of time alone. Whatever it is, but at time t, I'll give you a fixed vector. And that vector depends on a lot of things, whatever at time t is.
No, but in particular, the whole history of WT also to them. That's what it does.
Sure, but it's determined. Yeah.
Which depends upon everything up till like every 40.
Yeah, it varies in some crazy way. Yeah, it's a function of time, right? So it depends on.
But it's random.
Sure.
That's
yeah.
Then
yeah.
But because the lemma etc. will have to start including cross terms.
Yeah, we'll have to be careful when we analyze this. This is a valid stochastic differential equation. That's all we're saying.
Yes, but in the sense that this alpha t cannot be put in equal.
Not yet. Yeah. We have to look at the quadratic variation of this, which we can still talk about, which is basically asking how much does this PT of S, I mean, the formal notation looks like this, but what this is really saying is the integral of the stochastic part squared. So in this case, this would be this term times its transpose. So the integral of x minus mu t pt of x, t of x, length squared dt. So this is what we get from the Ito lemma if we do it carefully here. And now this we need to bound here. This is the quantity that, but remember the integral is not over all, this is not zero. The reason is because this is only over S, not over, it's not zero. So how do we bound this? And the game is in different ways of bounding this for different inequalities. But one bound that's generally useful is, we'll use Cauchy-Schwarz here, right? It's the sum product of AI, BI. So the Cauchy-Schwarz will tell me over S, I'm going to make this x minus mu t squared first. No, sorry. What I want to do is first, first let's write this. This is square. This is the length of a vector square, right? So I can think of it as the maximum of over unit vectors. Yeah. Of what? This. This zeta transpose x minus mu t ptx dx. I just took it inside, squared still. Okay, dt is not doing anything; it's just outside. Good. Now we'll apply Cauchy-Schwarz, and so this is still equality. Well, it's less than equal to because it depends on, I'm taking the maximum here. Now, wait, no, this is still equality because it's just the length squared. And then less than equal to now, this part of it, still max. Integral over S of zeta transpose x minus mu t square. I'll keep one ptx here. I think of it as square of square root ptx. So I keep one ptx here. And then times, excuse me, integral of just ptx. Okay? This became square root ptx squared. So we get the square root square here and the square root square here. And this is this. This is at most 1. And then this, if you look at it, is the largest eigenvector of the covariance matrix of X. Because this is asking for the maximum, or let me pull this out. Then it's zeta transpose X minus mu t transpose PTX, that's the covariance matrix times zeta. So this is the operator norm of the covariance matrix at time t times dt. And that's the key equation for many things here. That the change in the volume of the set for time t, didn't matter what the set was, is controlled by the operator norm at time t. A is the covariance, AT is the covariance matrix at time t.
So then it should be inequality still, right? Because
Oh no, I mean there's an inequality here. I'm just saying this.
but because
Oh, you're right, you're right. Yeah, sorry. Yeah. It's still just an upper bound. Yeah. But what does this mean? This means that the change over time t, if I go for time t and look at what is the difference between PTS minus P0s, it's like a Gaussian of variance, the integral of this operator norm from 0 to. Okay. So in particular, if this operator norm is bounded throughout, then it's just that bound times t. So a key factor becomes, can we bound this operator norm? Okay. We know, as I already said, it's bounded at time t by 1 over t. Let's say we're able to go up to constant time, then this is great, it's a constant. But, and we know it's bounded in the beginning because we started isotropic. What about on the way? Right? If it remains bounded all the way up to constant time, then you're done, because it's like, it's saying here that the total change is order of t, right? And t is constant, so total change is constant. We can make all these constants small enough, so your change is actually with some constant probability. That's all you need.
want this lemma to not be tight at small time. Right? Like if this lemma gives you an upper bound.
Yes.
But you know you want
Much, it should be much better.
much better.
In particular, at t equal to 0, we know it's just identity. And we want it to stay like identity as long as possible. Okay. So I'm reaching a point where I need to start summarizing. And so I'll do that. But hopefully this was not just sort of a too high level a glimpse. But let me do that. Yeah, I'll in fact show you the function which controls it. Yeah, that's one of the summarizing aspects. So the following is true. So this is a lemma where various papers improved the time range in which it holds. So for all s less than equal to t0, which is constant over log squared n. Okay, so not up to time constant, but up to time 1 over log squared n. The probability that the operator norm at time s, anywhere between 0 and, so s is greater than equal to 0, it starts at 0, is let's say greater than 2, right? It started at 1, probability exceeds 2, 2 is a constant, you can make it 1.1, is less than e to the minus 1 over t0. So in particular, when at this time, e to the minus log squared n, so certainly smaller than polynomial. We only need this to be constant, really, but we can only prove it up to this point. But let's see what this implies right away for KLS. So up to this time, operator norm is only 2, everywhere on the way. So when we look at how much did the probability measure of S change, it changed by some constant times the time, which is 1 over log squared n, square root of that, right? Okay, so that's tiny. It's still 1 over log n. So it hardly changed. It stayed between half plus 1 over log n and half minus 1 over log n. Fine. But we can only go up to time this. So the bound we get on the isoperimetry for PT is square root of this, which is 1 over log n. So that gives you KLS is log n. The current state of the art is KLS is square root log n. That requires a further argument. But to prove this, same process, that process, this process with inter, and the function we use is to prove this is instead of the operator norm, which is hard to control, you look at the exponentiate the matrix with some factor here, look at its trace and the log, and 1 over beta. Okay. So this you can show is at least the largest eigenvalue and at most the largest eigenvalue plus function, just depends on beta. And because this is a smooth function, you can take its derivatives, you can have fun with the Ito calculus, and then you have to prove something about semi-definite matrices and how they commute. Sorry? No. Yeah, not really. Yeah, no. Yeah. So I'm not going to show you this, how to control this, but the point is that this stays small up to this time. 1 over log squared n time. Yes, so this is a bound on operator norm, right? And actually it's not much bigger, it's operator norm plus a little bit. We can write it down, but yeah. So that's the point. So directly working with operator norm has been not so easy. We did it, but with weaker, smaller time bounds here, inverse polynomial bounds and so on. But this is a nice function too. Okay, so that's this root log n. You can use this to do various things. For example, you can understand how does mu t change, how does AT change. All these things you can write down, and those are straightforward. And one conclusion that comes out of this is if you do a slightly different analysis of different way to bound the change in the set measure, you can show that the measure of the original set is at most e to the power of the diameter squared times pt of s. This is for any set, not just a set of measure half. And no, it's the diameter of the whole support. And if you start with an isotropic distribution, for the purpose of what I'm going to show in a second, we can assume that the diameter is root n, order root n. So this effectively becomes e to the nt. Okay. Now, there was a breakthrough, as I mentioned, late last year, which says that for time up to constant, there is a constant less than 1, we cannot control the operator norm, but that's not known. But the expectation of the trace of AT square stays bounded. It starts at n, right? Identity, so trace is n, identity square, but it stays close to n. This is quite an intricate use of stochastic localization. It has to use the scheme recursively in intervals with multiple levels of boosting what's happening, the parameters going on and so on. But from this conclusion, you can actually show the following general theorem for any log concave distribution, which says isotropic log concave. So isotropic log concave P, the probability for x drawn from P that the length of x is smaller than epsilon times root n. So Root n is what you expect. This is what's called small ball probability. What's the probability on a small ball? Is smaller than a constant epsilon to the power of constant times n. These are different constants, but anyway. Okay, so it's exponential in epsilon. And this statement is equivalent to slicing. This was already known. This was known a long time ago. This optimal small ball probability is equivalent to slicing. To get this optimal small ball probability, this is enough. These are nothing to do with this method. This is a simple inequality. We need this statement to prove it, and then this equivalence follows from what are called M ellipsoids and slicing, an alternative formulation of slicing. Okay, so this is a theorem. This by itself may not look so interesting, but this also implies that the thin shell is log n. In fact, it proves that thin shell is log of KLS. And because KLS is root log n, we get log n. And so it actually, that's a very nice theorem in this paper, implied by this, which is that the thin shell constant is log of the KLS constant. Order of, yeah, sorry, less than equal to. Yeah. No. No, it's just the analysis. They use the same process. It's crazy, yeah, same process, but the analysis is very intricate. Yeah, yeah.
This is like controlling the second moment.
Yeah, so this is what this is indeed in Eldan's original paper. He was looking at trace of a to the k, for example, to control operator norm. Even though he wasn't doing isoperimetry, he was doing reduction from thin shell to KLS and so on, which loses the factor of log n, so it's kind of obsolete now because KLS itself is square root log n. But this is this is trying to control the moment. So yeah, if you remove this expectation here, it's not clear we can do this. But this is exactly what you need for this, and enough for thin shell also. It also turns out that this is not true up to constant, at least for this process. It's only true, potentially true up to 1 over log n. So there is another catch. 1 over root log n. So potentially you could improve KLS to 1/4. Otherwise, you need a fundamentally, at least a new process, maybe not a fundamentally new idea, but so there is some obviously unsatisfactory state of affairs. I mean, because the proof method didn't work out. After 2.5 hours, yeah. Yeah. This is not a stock submission, come on. But I wanted to mention 2 other things that that you may not see in the literature. One is that you can actually use stochastic localization to recover the Lovász-Simonovitch lemma. That takes a little bit of work. I don't have enough time, but I'll tell you what we do. So the changes are the following. Instead of just doing DWT, we're going to use a control matrix here, TT to the half, I'll say. Okay, it's going to be a well-defined matrix at each time t. And the way we will choose this matrix is so that the measure of the original set you're looking at, or some or function that you want to maintain one equality. Let's say. Remember, in the Lovász-Simonovitch, really we're trying to maintain one equality, right? As we bisect, we're going to maintain this one equality for the measures. And if you want to maintain one equality, we will choose this so that the change is orthogonal to that equality, and that's it. Okay, so basically, CT to the will look like I minus some unit vector transpose, defined by the current equality. Okay? Yes, looking at the current PT basically. And now this still gives you a Gaussian with T in front. And but the support now cannot prove is smaller than one dimension. Now, if you go to the limit, you recover one-dimensional measures. And in fact, yeah. No counting. Yeah, you just run this process and you get this. You get one additional property. You can actually show that these needles, the support of these needles is somewhat short. Their length is only about n to the 1/4. Okay, we get rather than yeah. So which also gives you things like KLS with weaker bounds, but that is tight. Turns out you cannot expect any method to do better than that because it's possible that there exist bodies that cannot be packed with all short needles. So that's one. The second one is minute, I guess, is the following. Maybe I won't even write. Here's an interesting problem. You all know about the classic Fourier-Combinatorial problem. I have a random matrix. What is its operator norm with independent entries? This has been studied very nicely. Lots of interesting generalizations as long as the distributions have basically equal variance or bounded variance. What if the matrix is drawn from a single isotropic distribution, log-concave distribution? So it's not Bernoulli, it's not Gaussian, it's not sub-Gaussian, but it's jointly log-concave. And I want to know its operator norm. So I no longer get to do epsilon nets so easily because the net is too big to. We don't have the concentration to drive it all down. I'm only asking about asymptotically. What's the bound on this? So what we can show is that that if R is drawn from nu, which is isotropic log concave, right? So the variance is 1 in every coordinate, right? That's by isotropy. Then the operator norm of R, so it's joint, right? The dependence, all kinds, whatever be the dependence. So for a convex body, whatever, yeah, is so with you can get probability bounds. Let's say with probability 0.9, this is bounded by up to constant by root n log n. It's just think of this as a single. Yeah, it's an n square dimensional isotropic log concave, but I'm writing it as a matrix and asking this operator on. It's like generalizing other Shreni or whatever you want to, for the converge, but and so the right answer should be root n, and this is what I can prove right now with stochastic localization. Yeah. So the covariance matrix in n square dimensional space is identity. Is n squared.
I have a pairwise independent distribution of entities, but if the joint distribution is log concave, they basically give me the same spectral norm.
Well, log n right now. Yeah. And this is you've more or less seen all the techniques I need for this. Yeah. So is this? I mean, do you think it's interesting? Yeah. I mean, it's probably not the right answer, but yeah. Hopefully, yeah. So, there seems to be. I mean, one that I would like to do is the certifiable hypercontractivity, which we know is true for T strongly log concave.
Yes.
But can you imply?
Yeah, it seems like it's designed for it. No, you want to
But probably I should stop. No. Thank you.
Thanks, Santosh.
Please.
Again,
Yeah, because each entry is a variance 1. Maximum of the column norms? That will be actually be order root n. But we're talking about the spectral norm, right? So in principle, all of them could align and you could get n. The trivial bound would just be would be n.